What is the difference between average and instantaneous acceleration? It is the same as that between average and instantaneous velocity. Average velocity is the constant velocity needed to cover a certain displacement in a certain time. Similarly, average acceleration is the constant acceleration needed to produce a given change in velocity in a given time. Instantaneous velocity is velocity at a particular instant. Similarly, instantaneous acceleration is acceleration at a particular instant. It is a value which is shown on an accelerometer and it is represented by letter A. Let's explore these concepts further by looking at a situation. This table is representing motion of an object that is moving at changing speed. So in the first column, time interval is given and these are the value of speed at these times. Let us calculate average acceleration over these marked intervals from 1 to 3 seconds and then from 4 to 5 seconds and between 6 to 7 seconds. So in the first 3 seconds, the speed changes from 1 to 3. So the average acceleration would be the difference in the speed over the time taken. So that gives us a value of 1. For the second time interval from 4 to 5 seconds, this is a change in speed of 4 over a time interval of 1 second. So the final value of acceleration would be 4 meter per second square. Similarly, for the last time interval, the acceleration is 2 meter per second square. What about the average acceleration over this bigger interval from 0 to 8 seconds? So the velocity change is 20 over 8, which gives us 2.5 meter per second square. We can consider these accelerations over smaller time intervals to be instantaneous accelerations, and this acceleration calculated over the interval from 0 to 8 seconds to be the average acceleration over the whole interval. And what do you notice by comparing this number of 2.5 meter per second square with these three numbers? We see that generally average acceleration is not equal to instantaneous acceleration at a certain time. How can we obtain average and instantaneous acceleration from a graph of velocity versus time? In a similar way as we obtained average and instantaneous velocity from a graph of position versus time. Average rate of change of an object can be obtained by looking at the slope of secant line of a graph. An instantaneous rate of change of a quantity can be obtained by looking at the slope of tangent line of a graph. This is a velocity versus time graph. If we want to find out average acceleration over the given interval from point P to Q, we will draw a secant line and look at its slope. But if we want to find out instantaneous acceleration at particular time, let's say at this time interval, we will need to draw a tangent line at that point and look at its slope. Similarly for here, I will draw a tangent line like so. You can see that the slope of the secant line is not in generally matching the slope of the tangent lines. So average and instantaneous acceleration are usually not equal, unless there is a special case which is shown in this graph. This is also a velocity versus time graph, and if you want to find out average acceleration, you will draw a secant line. For instantaneous acceleration, you will draw a tangent line. But any of these lines that you draw, they will all overlap on the graph itself. So in this case, average and instantaneous acceleration are equal. This is the case when the acceleration is constant, because slope of this line is constant. In the previous graph, the slope was changing, so instantaneous acceleration was different at different locations. Let us look at motion diagrams and acceleration. These are 4 different motion diagrams. Take a minute to figure out in which of the motion diagrams the object is moving at constant velocity, when is it speeding up, and when is it slowing down. In B, the distance between each diagram is same, which means it's moving at constant velocity. In C, the distance between the diagrams is increasing, which means it's speeding up. Similarly, for D, the distance between each diagram is decreasing, so it's slowing down. What about A? Well, the object is not moving at all, so all the diagrams are overlapping here. So this is also a case of constant velocity with the value of 0. Let us focus on the motion diagrams with velocity vectors for the two situations when the object is speeding up here and when it is slowing down here. These red vectors drawn from one dot to another are velocity vectors. And as the object is speeding up, these velocity vectors are becoming bigger. Similarly, in this diagram on the right, the object is slowing down, so velocity vectors here are becoming smaller. We will draw one acceleration vector for each of these motion diagrams. In the left diagram, acceleration causes the object to move faster, so it is making these velocity vectors to become longer. This implies that the acceleration vector should be pointed to the right. So I will draw the acceleration vector for the diagram on the left like this. For the second diagram on the right, acceleration is slowing down the object, which means it is making these velocity vectors smaller. This implies that acceleration should be opposite in direction to the velocity vectors. So in general, if the object is speeding up, the velocity vectors are becoming longer in that direction, then acceleration vector will also point in the same direction. And if an object is slowing down, the velocity vectors are becoming smaller in length, then the acceleration would be opposite in direction. Let us draw a motion diagram of an accelerating car. These are 4 scenarios here. In the first one, the car is at rest and then starts to speed up. In the second one, it slows down to a stop. In the third one, it also starts from rest and speeds up. So it is similar to situation 1, but it is now moving to the left. Car in diagram 4 is similar to car in diagram 2, but it is moving in the opposite direction. So it is also coming to a stop. Let's draw a motion diagram for all these 4 scenarios. Case 1, the car is speeding up, which means the dots are becoming farther and farther apart, and the velocity vectors are becoming bigger. In the second one, the car is coming to a stop, so it's slowing down. So the dots in the motion diagram are becoming closer and closer, and the velocity vectors are becoming smaller. In the third one, it is speeding up, but now it's speeding up to the left. So dots are getting farther apart, velocity vectors are becoming bigger, but they are pointing to the left. In the fourth case, car is moving to the left, it is coming to a stop, so dots are getting closer together, and velocity vectors are becoming smaller. So this is the final output. Let's draw acceleration vectors for all these 4 cases. Case 1, velocity vector becoming larger, pointing to the right. So acceleration should also point to right. Second case, velocity vectors are becoming smaller. The object is moving to the right. So acceleration should be opposite to it to make the velocity vectors smaller. In the third case, the velocity vectors are becoming bigger, pointing to the left. So acceleration should be to the left. In the last case, velocity vectors are becoming smaller to the left. It means acceleration should be to the right. For complete analysis of the signs for the situations, we will choose a coordinate system. So for this problem, let us choose positive direction to be to the right. According to this coordinate system, velocity is positive for first diagram and acceleration is also positive and it is speeding up. Similarly, in the second diagram, velocity is positive but acceleration is negative and we can see that it's slowing down. In the third one, velocity is negative and acceleration is also negative, but the car is speeding up. And in the last one, velocity is negative, but acceleration is positive and it is slowing down. A few things to notice about the sign of acceleration and information about speeding up or slowing down of the car. First of all, whenever acceleration is negative, it's not always slowing down, as in case second and third. Only the sign of acceleration alone cannot determine if an object is speeding up or slowing down. What can we conclude about speeding up and slowing down of the car by looking at the signs of both acceleration and velocity? Let's look at the scenario where the signs of velocity and acceleration are same, as in the first and the third case. We notice that they are speeding up. In the second and the last case, the signs of velocity and acceleration are opposite, so the cars are slowing down. So the conclusion is, whenever velocity and acceleration have same sign, the object will speed up, and whenever velocity and acceleration will have opposite sign, the object will slow down.